Yes, great. All right, so now it's time to talk about diffusion tractography. And so just as a first slide, this is from Flavio, actually. I like this slide. So tractography is everywhere. If you go to a convention center, you go to exhibitors, people use tractography to sell MRs. They use it, as you know, in many international grants now, the Human Connectome Project, the Developing Brain Project, for 3D art, 2D art, and even on the cover of rock band magazines. So I want to show you what's under the hood of tractography in the next 30 minutes and show you the basics and also some of where tractography is going. So here's the curve of diffusion MRI publications in yellow and tractography publications in blue. And so as you can see, it was invented and first published at the end of the 90s. And since then, it's quickly picking up. And as connectomics, structural connectivity, and the Human Connectome projects are really scaling up, we can expect this curve, if we update it, to be really rocketing and taking an exponential curve up. So tractography is very present. It's being used a lot in connectivity and to study specific white matter bundles, as you see here. And so the goal of my talk today is really introduce the basic principles to give you an intuition about what is deterministic and probabilistic tractography. I'm not going to have time to cover all the algorithms out there, but just give you enough intuition as what are the important parameters to know about as a user, and also then get into the precautions, the limitation, and some of the challenges for the tractography and the connectivity world in general. So how do we go towards optimal tractography? And we've seen different talks this morning. So we have to see the tractography pipeline as a whole. And before recently, a lot of these different bricks of the pipeline were out of synchrony. Acquisition people on one side, reconstruction people on the other side, tractographers on the other side. And so to really get an optimal processing pipeline, we have to see these as a whole block. And so all the artifact correction, the state-of-the-art acquisitions, the good fiber crossing reconstructions are critical to have optimal tractography. And what I'm going to talk about today is really the later stages. But keep in mind that you need a good optimal processing pipeline from raw DICOMs coming out of your scanner to all the way up to the tractography reconstruction. So, tractography, and a new term, the tractogram. The tractogram, if I use it in the talk, is the set of all streamlines, all tracks, all fibers assembling are part of the output of tractography. So this is a tractogram. So many different parameters are hidden from the user if you launch tractography, such as step size, angular constraints, interpolation, masking, and seeding. I'm going to mostly spend time on masking and seeding and try to give you intuitions for the other parameters. So the first critical thing for tractography is seeding and masking. And there are different strategies. You can have a region of interest strategy, where you could imagine seeding tractography from a region of interest and going everywhere else. You can have a whole white matter seeding strategy, so that's the picture in the middle. Or recently what we've seen appearing is seeding from the white matter, gray matter interface, as you see in the third figure. And so just a word of caution, most of the algorithms or most of the public software out there use fractional anisotropy as a way to mask and initialize tractography. And here's an example of an FA map in a coronal slice, and I'm just going to show you a few thresholds on this. So if you threshold at 0.2, you see that you still have holes in your white matter. And these holes are not because you're in CSF, it's because you're in crossing. So my mouse is not working. Is there a way to make the mouse work? But you see these locations in the centrum semioval. Does that work? No. Here in the middle, where you have crossing from the corpus callosum, cortical spinal tract, and SLF, where FA is actually lower than 0.2 there. You have three-way crossing fibers, very spherical like these DTI tensors, and your FA is quite low. And if you keep thresholding down, so 0.15, usually the default so default parameter is 0.15 or 0.2, you still have holes. And at 0.1, you still have holes. So just that's a word of caution. You might have the best data out there, but if you just wrongly seed your tractography or mask your tractography, basically these are locations where your streamlines will not even be allowed to propagate. They'll stop. They're not going to go through these locations just because they're not part of your masks. So keep that in mind. So nowadays, a recommendation, and during my talks, little recommendations will wipe through the bottom here. Most state-of-the-art tractography pipeline try to use the T1 weighted image, which is most often acquired with your diffusion. So you have a higher resolution there, typically at 1 millimeter isotropic. Tools to segment out the white matter, CSF, gray matter have improved greatly. So you have good partial volume maps of white matter, CSF, and gray matter. And registration tools also have become much better to align your T1 and your diffusion data. So do use your T1 instead of thresholding FA. Then we get into different tractography algorithms, and I'm not going to have time to cover them all. I'm going to cover the intuitions behind streamline deterministic, streamline probabilistic, and probabilistic-based tractography. There must be at least 200 papers out there. There are good review chapters on this subject if you look me up on my webpage and in diffusion books in general. But keep in mind that as we're going to do tractography, we're going to track through a grid, a discrete grid, on which you have multiple directions. As we saw in Flavio's talk, we're going to use multiple fiber reconstruction from a high-order model. But look here in the corpus callosum. I wish my mouse could work here. But right at this middle here of the corpus callosum, this is the biggest white matter structure in the brain, and you have barely 3 voxels wide there. So you can imagine that if you're starting or seeding from the motor homunculus out on the cortex, and you're a commissural streamline or fiber that has to come down and bottleneck into the corpus callosum, you can see this is an extremely ill-posed and difficult problem for tractography. I'm just going to throw some numbers out there, but let's say you're initializing with 1,000 voxels out on the cortex, you come down, and everybody has to go through 3 voxels and then come out of the corpus callosum. So that's like a 1,000-lane highway coming into the Manhattan Bridge into New York City on a 3-way lane to New York City and then exiting off the brain. So you can already imagine that this will cause a lot of problems for tractography. Right? So we're tracking on a discrete grid. We're going to have to take, from a seed, take small step size. You have to choose this step size. And we're going to interpolate and have angular constraints to decide, are we allowed to make a 90-degree turn or just a 60-degree turn? And so I don't have time to get in all those details, but one recommendation that is out there is for step size. If you're using just a straightforward linear step size, you use about 1/10 of your voxel size as a general rule of thumb for recommendation. And if you use a second-order integration, such as Runge-Kutta, you can have a little larger step size. And in general, a 60-degree angle is a good recommendation for deterministic tractography. But some recommendations are in these references here if you want to look at more details here. And in terms of probabilistic tractography, we'll see in the next slides there's two ways to see probabilistic tractography, but in a sense here, instead of just always choosing the principal maximal direction, so the maximum amplitude of the fiber ODF, we're going to allow ourselves to sample this fiber ODF orientation distribution. So either you see it as a continuous sampling of the fiber ODF representation, or as a way to explore the uncertainty in your diffusion data. So these are the 2 branches, 2 ways to see probabilistic tractography. The first one is the one that's mostly implemented in MRTrix, DISPy, Explore DTI, where you see the fiber ODF as a continuous representation of orientations, and then probabilistic tractography is a way to sample this fiber distribution. as opposed to the second category of techniques that are mostly based on Bayesian modeling and bootstrapping, where you see fiber orientations as being sampled in a cone of uncertainty. So your diffusion data has some sort of uncertainty in your principal direction. You can estimate, this uncertainty and take that into account into your probabilistic tractography algorithm. And so if we take an example here on the cingulum bundle, and we take a single voxel at the middle of the cingulum bundle, if we initiate a single seed there with a 0.2 millimeter step size and a trilinear interpolation, you see the pathway that it's created. So it's not a fully connected cingulum bundle. It's quite challenging. It's quite tiny. You have a high curvature. And so instead of that, if you use a probabilistic approach with 100 seeds in the same voxel location, well, you'll see that at the beginning, most of the streamlines are on top of each other. And then as you get into the curving area or the fanning part near the cortex, you start exploring and sampling your fiber ODF distribution more. And you can also see probabilistic tractography as a way to count the number of times each voxel has been visited. So you can see these heat maps that we often see in the papers. And so this is just another way to visualize or to represent probabilistic tractography. So as a general statement, it's been shown in several papers that there are trade-offs between deterministic and probabilistic. It's hard to say if one is better than the other. I really don't like saying things like that. But it really, as a trade-off, it does recover a lot more of the spatial extent, more of the curving part of white matter bundles, but at a price of generating potentially more false positive bundles, and thus needing more knowledge of the anatomy and more exclusion regions to clean up your tractogram. A small parenthesis about DTI versus Hardy. Flavio already showed some nice figures. Here's just another one. Again, as a general statement, Hardy or multiple crossing fiber directions reconstruction will allow you to get better curving, better fanning, better penetration under the gyrus, but again, at the price of potentially generating more false tracks. So if you're very meticulous at building these beautiful figures, cleaning up the mess, it looks amazing, but it hides a lot of the false positives that are created by these more flexible, more exploratory probabilistic algorithms or fiber crossing algorithms. So let's get into the precautions and the limitations of tractography. And so the first thing, if you're not careful, let's say you just use your FA threshold and you launch 1 million seeds and do tractography, is a lot of your seeds are going to die not reaching the cortex. They're just going to die along the way. They're going to finish in unrealistic anatomical areas. They're going to end in the ventricles. They're going to stop in the middle of the white matter. And so these are what we've called in our tractometer paper as the no connections. They're quite easy to post-process. But nowadays, with techniques using the full T1, as I'm going to mention later, we can remove them as we're tracking and thus less contaminating our tractogram. So the solution here is, again, to use our T1. As you see in these images, a T1 weighted image has lots of voxel with partial volume. Voxel with half white matter, half gray matter. So now tractography has the potential to use this information to prevent stops in the CSF, if we have a good CSF segmentation, to force streamline to finish in cortex or subcortical areas, or exit the brainstem. And so if you do so as you're tracking, this will reduce the number of no connections. We're missing a word here. And so that has, and if you go one step further and take into account the partial volume effects, so here's an example, just a toy example. Let's say this is just a small white matter band surrounded by CSF. It's quite hard for tractography to get around the high curvature, not to stop in all these partial volume effects. And so if you use this information into account, you can see that you can reject streamlines that stop prematurely. You can enforce streamlines to not stop in white matter. And so the green fibers here are the fibers that survive. So there's a lot more potential here that you can explore small white matter bands that are contaminated with partial volume around them. You can better penetrate under the gyri. And so that is a very effective way to use the partial volume maps from a T1 weighted image. So it helps reduce no connections, and it improves coverage of white matter in general. And so this term now has been quite accepted in the literature as being called ACT, or ACT, anatomically constrained tractography. It's a way to inject priors in your tractography process. So MRTrix has a solution. We have a solution implemented in DiPi and SilPi, where basically you leverage, again, the partial volume maps estimated from your T1 weighted anatomy. Another big problem, especially for connectomics and people using streamlines to build connectomes. Let me just walk you through a little problem here. We're in the middle of the corpus callosum, and if we seed aggressively in the whole white matter, and this is illustrated here by these little spheres, and we imagine that each of this sphere will create a streamline, well, what will happen? What kind of bias will be produced by white matter seeding tractography? If you think about it a little bit, it's easy to see that large, big volume bundles will be overrepresented. There'll be more seeds placed into them in white matter seeding. They'll produce more streamlines, and they'll turn out to be overrepresented in your tractogram. So if you're just blindly counting tracks, the probability that a track is part of corpus callosum, CST, or SLF is much higher than the smaller tracks. And this is a seeding and shape bias. And one of the ways it's been shown to reduce this problem is to use seeding from the gray matter white matter interface. It comes with its lots of problems, but now instead of being proportional to volume, seeding will be proportional to surface area of cortex. So a larger cortical surface area will generate more seeds and potentially more tracks, which is a little bit more biologically inspired, because this is where the neurons are, and this is where the neurons are making their projections in white matter. So it's not solving the issue, but if you're actually quantifying the distribution of tracks in your tractogram, this helps reduce the overrepresentation of large, big, easy-to-track bundles in your tractogram. So the next generation of tools that's coming, and it's not easily done yet. I am not aware of a public software that's doing that yet, because it is a challenge. It's the next generation of these tools will use the cortical surface and the actual mesh to initiate tractography. And if you have the cortical mesh and the knowledge of the normal to the surface, this can boost tractography to better penetrate inside the white matter and reconstruct much more realistic fanning structure near the cortex. So this is coming. Different groups are working on this strategy, and just as we're using the T1 weighted image, now we're going to use the free surfer or other cortical parcellation or other cortical mesh extraction techniques to initiate tractography. And so just to throw it out there, we're still very bad to track around the deep structures, around the cerebellum, around the insula. Let me just zoom in here. This is a T1 around the insula. You can see it's just a big blur. You have the putamen and the insula on the other side. And so if we zoom on the FA, you see this thin white matter strip there. Extremely challenging for tractography to even be able to go through this, just in terms of spatial resolution and partial volume with gray matter and CSF around it. So there's clearly a position bias in the brain. We're good at reconstructing easy-to-track fibers. Now we have to start tackling through better acquisition, better modeling, harder to track regions, and these are some of the locations where we're still challenged. Even more challenges. The false positive challenge. So what we also call the invalid connections. How can we be sure when we reconstruct a fiber bundle that it's not in the anatomy books or not in the atlases that we know, that's not in the monkey brain, for instance? How do we know it truly exists? It's reproducible. I can find it in every brain. But can I trust my tractography? Or that's just an invalid connection? And so a couple years ago, we started this ISMRM 2015 Tractography Challenge in which we build a synthetic phantom brain with 25 realistic existing bundles from a Human Connectome Project brain. So this was just a fake numerical brain, but in which we had the ground truth bundles and also the ground truth endpoints, and we could start simulating diffusion images to have a feeling of where do things go wrong and how often do we make these invalid connections or these wrong bundles. And so the good news, the first good news is that most tractography algorithms, and we got about 100 tractography algorithms submitted, most tractography algorithms reconstructed the big bundles. So the smaller bundles like the interior commissure and the posterior commissure that were very tiny, very challenging, most techniques missed them, but most techniques found the existing bundles. But the sad or more challenging message that came out is that for every bundle that we found that existed, we generated more or less 4 to 5 invalid bundles, wrong bundles. And so that was a finding that was striking, and the first, nothing new here, but quantitative. And so what was happening? What's happening in there? So let me just show you a little video of what I think is what is happening. So in a nutshell, we're getting a lot of bundles that look real. Okay, some of them look real, look like real anatomy that you guys have seen before, but they're just not in the phantom, so that's something. But a lot of them just look wrong, completely wrong, asymmetric, taking wrong turns. They're very dense, very thick, and in locations where they were not in the original phantom. And so what's happening is this, again, this crossing fiber problem. We think we've solved it by finding multiple directions, but it's way beyond a single orientations or a crossing information. We have a lot of these voxels where the ODF for all these configurations is basically the same. So we have no way to see if we're in a kissing or a bottleneck situation or in a pure crossing situation. And here's just a little video of 4 bundles that are in the phantoms. So the corpus callosum, the cingulum bundle in red, the SLF here in green, and the cortical spinal tract in blue. Let me play it again. And one of the bundles we did not put in the phantom is the Aslan tract. And I'm not claiming the Aslan tract doesn't exist. I'm just saying, just out of this geometry, it's very easy for tractography to start here, to come along the cingulum or the cortical spinal tract, and then jump into a bit of the cortical spinal tract, and then jump into, again, a bit of the corpus callosum to finish here. So it's very easy to create unexisting anatomy from tractography if you're not careful. And you have so many crossing fibers, and we're pretty good at finding them now locally, that it's actually very easy to connect them wrongly. And so I think that's a clear message that there's a real open challenge for tractographers to try to tackle this invalid connection problem. But just as a side note, it's a very hard thing to validate. And so through Klingler dissection, we were actually, and I always thought this was a false positive. I always thought this was an artifact of a tract starting from the deep nuclei, coming into the corpus callosum and up to the superior cortex. Well, through Klingler dissection and very careful top-down approach done by our neurosurgeon Silvio Sarubo in Italy, we were able not to find exact connectivity results, but find the existence of this tract that I always thought was a false positive. So this is a real validation challenge, and do we need to do that for every single bundle in the brain? Well, this is a question I leave open for out there. But there are different ways to tackle the validation challenge. We saw one with ex vivo acquisitions. Here's another one with Klingler dissection, with postmortem macroscopic dissections, and potentially other ones with other phantoms and numerical phantoms. And I want to finish with this maybe exciting new avenue for tractography. Is we've seen this great talk by Els and diffusion microstructure and time-dependent diffusion imaging being out there to maybe start estimating the diameter or the distribution of axon diameters. Well, could this help tractography? Well, we believe it will help. So imagine that we have a crossing here, this little ODF, but that for each of these principal directions, we have a diameter estimation associated with it. And one of the peak is a smaller caliber like axon, and the second peak is a bigger caliber type axon. Well, if we have these caliber indices, well, now we can take a smarter decision as we perform tractography. We're not going to try to connect just orientations that are similar to the incoming directions, but we're going to try to connect directions that are similar in terms of orientations and caliber information. And that's the new term and new developments going towards microstructure-informed tractography. And so just a little toy problem again. Imagine a pure kissing problem here with two axon diameter distribution, one small axons, 2.4 microns, the other at 2.88 microns. And here you see the ground truth peaks colored by their axon diameter. So your eye is already doing the right tractography here. It's very easy to discriminate the two. But the ODF is completely blind to this, right? This is a pure kissing problem, and any of the four bundles here, the two true ones, but the two wrong ones could be reconstructed. And that's what we see in practice. In the top row, if you do standard tractography without the microstructure information, you can basically generate every possible wrong and valid track and about a 50-50% distribution. But at the bottom, and this is just a proof of concept, using the caliber information, you can really start discriminating the two distributions, the two bundles, with their specific caliber information. But this is assuming very good microstructure estimation, good acquisitions that we can do in vivo, and we're far from being there. So in conclusion, just as overall recommendations, don't use tractography as a black box. Use your T1 weighted images. Public softwares out there do use it now. Registration and segmentation of partial volume maps of CSF, white matter, gray matter are very good nowadays. Tune parameters in function of your application. For instance, if you're just looking for the fornix, it's not the same problem as looking for the arcuate fasciculus. The fornix is near the ventricles, near a lot of partial volume. It's a small, tiny, curving bundle. It might not have the exact optimal parameters as tracking the arcuate fasciculus. So keep that in mind. I'm not the one that said this, but there's a few papers out there saying, be very cautious about counting tracks. I've shown you biases here. Track count to me is just correlated with easiness to track. The more tracks you get, it's just the easier it is to track, or the bigger the bundle. So be careful with that, and I would really not use this term as connection strength. So interpret results with cautious, and I think the future will bring us more anatomical priors, better validation, better regions of interest, multimodality, and hopefully microstructure-informed tractography. So here's a small list of some of the open challenge, I think, for tractography. Better spatial and angular resolution to track through hard, small, difficult areas of the brain. Tackle the invalid connection and false positive challenge, so with better validation, with better phantoms, and using all the information and all the priors we can to tackle this problem. To hopefully, with that, try to make tractography more quantitative, so that one day we can really have a measure of connection strength between two areas. So thanks for your attention, and thanks for the inviters again.
Okay, so now I would like to call the speaker of the morning, so we can open the discussion. And I know you are looking for lunch, but please resist a little bit more. And now is your time. So now you have the opportunity to ask all the questions you always wanted to ask. And yeah, we need some chairs, it looks like. So, okay. Yeah. Cozy.
There's room over here.
All right. Sorry, with this slide it's not really easy to see if anyone is standing, but any question? Feel free to ask any question you are interested in. For example, you're starting a new study, you want some advice for how do I set up the acquisition, what kind of preprocessing, if I have to make a choice, which one are the most important step for preprocessing. Yep.
Definitely the right question, but with 200 pipelines, each of which has 15 steps, what do we do?
Alex?
So you mentioned, sorry, I can't really see with the light here, but so you said something about 15 steps, and what do we do? Well,
No, the issue is, let's say that a full pipeline, taking all of the examples, i.e. the NYU group or the FSL group, we've got, let's say, 10 steps, each of which has a set of 5 or 6 parameters on each step that's within that set. How do we identify very good solutions? I'm not even going to worry about optimal. How do we identify very good?
Well, that's a good question. I mean, to some extent, it's also based on experience and guidelines that people that have worked in this area for many years say, like, okay, I suggest you do this or this setting. Admittedly, it can depend a lot on the data itself. So obviously, if you have, let's say, a 30 directions diffusion data set with a b-value of 1000, then some of these higher order models cannot be used, at least not reliably. So this is information that you need to know in order to start making or planning all the different steps towards processing and analysis. So obviously, a suggestion is, talk to the team member that has some experience there, or get advice from a colleague there.
If I may, that was one of the questions I had maybe 5-6 years ago, and the tractometer platform, and I'm pitching a bit for my own idea, but the idea was to make this possible as a community. So the tractometer, in principle, can either take in diffusion data or local reconstructions or a whole tractogram, and then run most of the publicly available software out there on Computes Canada clusters to try to explore the space of all parameters. And I think as a community, we should get inspired by the machine learning community and probably better search the space of hyperparameters more smartly. But for this, we need validation data sets on which we can truly quantify improvement. And I'm not sure we're there yet. We have different toy-like phantoms and different versions of phantoms, but if we have a good standardized phantom in which we can benchmark and run all the different acquisitions, all the different pre-processing, all the different local reconstruction, and turn on denoising and no denoising and no motion correction and motion correction, and start exploring this highly high-dimensional space of hyperparameters, we'll get there. But I think we need to do this as a community. It's way beyond a singles lab task, I would say.
I also wanted to add to that there's a lot of pre-processing steps, you're right, but a lot of these, like denoising, decupsing, as Alex said, they're essential. And I think one thing that's very helpful, as Alex also said, are looking at residuals, look at what the effect is of each step. If it's denoising, is it really only noise you remove? Is it gips you remove? I think that really helps when you look at the data, as Alex said.
So one thing that you're probably all aware of, but is that this is not exact sciences, right? There's a lot of ifs and buts and model assumptions and data quality issues. But one thing that people also tend to forget is, what is your research question, right? So which analysis strategy do you need? Do you need to go for the full-out fancy connectomics pipeline if you're just addressing or try to address a question about some region in the brain? Okay, so it's highly dependent on the research question at hand. I see there are some questions there, so.
Okay, this is a bit of a very general question, but would you have any special recommendations or considerations for longitudinal data, especially thinking that there is some attrition over time, so not all data is available for all subjects?
Okay, well, I will start with something very obvious. You want the best possible data and you want the most stable data across your study. Because sometimes I'm part of a multi-center study and people decided to change, for some center, decided to change the scanner. Longitudinal becoming more difficult in this case, as you can see. So first of all, the quality of the data is important. It's also very important to do quality control of your data. You need to have a protocol that check that along your study nothing is happening to your coil, for example. Sometimes your coil get broken or you have other problems. And that is important to have a reproducible data. That's the most important thing. So you want to have a reproducible result. And then there are many different ways of analyzing the data for longitudinal differences. I think that in the afternoon we'll talk more about statistical analysis for group comparison and also development and longitudinal. So there will be more about that later. But definitely, I would say the quality of the data is one of the most important things for any longitudinal study.
Just another thing that's kind of obvious, but you brought it up. But you should probably program in a certain attrition rate in your study because you know you are going to have some attrition. So many longitudinal studies will scan more than they think they need at the beginning. Would it be possible to turn the room lights on?
Yeah, also an obvious thing to do would be a phantom that you repeat over time. There's a few phantoms out there. There's one from, I think, Kiba that has like standardized diffusion coefficients, but you can also make your own ice water phantom.
Hi, also a general question. I'm starting tractography study. I used to do fMRI. So I'm using fMRI-based seeds to do the tractography. Any words of advice? General.
I think there's an entire talk on that this afternoon, actually. So, well, I won't say too much about it, but you may in the end up. There's a lot of things you can do. Like you can take your activations and extend them into the white matter, or project them onto the gray matter white matter surface, so that you know you're starting in a good way, like Maxime talked about. But I think Fernando's talking about this in the afternoon, so you'll have a lot more information about it then.
But Maxime might have a comment because he said that the
I was
gray
gonna
matter,
say,
white matter interface might be.
I was going to say the same as Jennifer just recommended. I would be cautious about the shape bias, so that your big fMRI blobs will have a bigger intersection with the white matter, will generate more seeds, they'll generate more streamlines. So if that's something you want, that's fine, but that's definitely something to consider as opposed to a small fMRI blob. So there's a shape problem and also how to deal with properly intersecting with white matter. Because the other thing with the white matter gray matter interface is these are locations where diffusion is low SNR. So lots more directions there, maybe a higher uncertainty on your principal direction. So it helps forcing the normal direction. If you have the curvature information, it helps to force it in that direction to at least initialize your tractography in the right direction towards the white matter.
Okay, thank you.
If I can say something related to that also, I have a kind of a preference when I try to combine fMRI and diffusion, is not to consider the fMRI blob like precise at the voxel level, but more looking at what anatomical region is actually activated, because you might have a lot of variability due to the analysis you do on fMRI, like for diffusion, and so I think it's much better to look at the anatomy overlapping than more than actually the voxel to voxel overlapping. So just using as a pure seed for tracking, I think is kind of risky. You might miss something, or you might see too much, like Maxime said.
My question goes more into the direction of interpretation of changes in diffusion parameters, because over the last years there has been a growing literature on like really rapid changes in, for example, mean diffusivity or something related to learning and memory, and that maybe even diffusion parameters could be a proxy for structural plasticity. Maybe you could speculate on the underlying mechanisms and how you would go about for actually centering in on the candidate mechanisms that could be participating in this effect.
I'll start. So one of the theories with plasticity is that you can get increased myelination, and that would certainly change the diffusion parameters, even the FA or more sophisticated model parameters. Well, again, you have to be careful when you're going from a change in a computed mathematical equation to a real biophysical change. But so that's one thing. I think there's been a little bit of debate about what we're seeing in the short term and whether that's actually a permanent structural change or just a temporary cellular activation-based change. And I'm not an expert on that. So I guess you just really need to be careful in your interpretation of what exactly is going on biophysically.
Yeah, if I can add to that, and I don't know if maybe it's also this afternoon and there's a talk on that, but if you see changes, for instance, in FA, it may be helpful to look also at radial and axial diffusivity to see whether it's in predominantly radial. You may be more confident that it has to do with myelination. As Jennifer also said, if you have more than just DTI, the more you acquire, you can do advanced modeling and then maybe become anything wiser. But I guess it's always helpful to look at the data in as much data you have acquired. If it's FA, also to look at radial and axial and try to get more insight from that.
Can I ask? No, not ask. I will add. So this is actually a very interesting question, because there's things coming up that is even in very short times, in actually minutes or something like that, you actually can have a change. And then it is that here, when you observe this kind of change, and then the challenge is like to say that this has nothing to do with the acquisition, it's something real anatomical. But then the fun part actually starts, because now you're going to be the Sherlock Holmes trying to dig out what is the information. And then you can wondering if that could, for example, be myelination. Could myelination change so quickly? I do not think so. But there could be other kind of microstructural features that will change and maybe change the extracellular environment. And that is the thing you need to find out. So therefore, for this kind of thing, I think it's the most simple thing is to use the tensor, which is very sensitive, and then from that one try to use, you can, for example, look at histology or something like different kinds. Of course, if you have a child developing, then you have a challenge looking at histology, but maybe you can have an experimental animal model and then try to dig out the information, because it might be something that we cannot see today or we are not thinking of today. A lot of things are going on, and that could be the astrocytes and then how all the processes going on there that is highly dynamic. And what we also experience in this dynamic time is that sometimes you see things popping up, changes, and then they disappear again, and then there's something else happening. So the brain is much more dynamic than we absolutely are thinking of today. So it's interesting.
Thank you.
starting a new project where I'm segmenting out a few tracks based on random regions. And so basically, how do I know when/where certain tracks overlap? And is there a software that I should use to identify these overlaps?
Can you repeat? What is it you're going to do? So,
I understand.
no, you okay.
Yeah. Well, you can repeat.
Okay. So I have a brain, and we have the tracks, and I need to segment out certain tracks based on like the region. And so we have tracks, and I don't know when they will overlap sometimes, and so I want to identify when they overlap and how to address them.
It's a tough question first, and I don't want to advertise any tools here, but there are, I would say, 3 or 4 tools out there that you could use that were mentioned in the talks. Maybe one thing I would start with is Flavio presented the NUFO map, the number of fiber orientation maps. So as you start exploring your white matter and the intersection between 1 or 2 bundles, is the overlap creating just a single peak because it's fibers that are actually kissing or bottlenecking? Or the overlap is generating pure crossings and location where the NUFO map would give you a 2 or a 3. And so I would have both a local approach to it as well as a track dissection approach to it to try to zoom in some of these kissing, crossing, overlapping regions. Definitely with a multi-fiber reconstruction algorithm. I don't know if that's a good answer.
I just want to add one little thing, is that if you already have a research question for your study, probably you already know what kind of track you want to dissect. And if you know already what kind of track, probably the easiest thing to do is just study their anatomy on previous publication, if there are postmortem dissection, functional activation, because you don't have just to follow the single DTI or the spherical deconvolution, whatever methods you use for tractography. You want to see how this match with clinical, with fMRI, as I said, and other study. And when you start to build your kind of idea where the tracking is going, there is going to be much easier. But in theory, you need to know the anatomy of the track. There is not a button to give you a boom, this is the right track. Not yet. We are not there at that level. Almost. Well,
I was like mainly concerned about the software, but thank you.
I have a question about, I don't want to say bad data sets, but like legacy data or something that's being acquired across multiple sites where you kind of have to go with the person or the site that has the poorest abilities, and so stuff like that we run into a lot with not having optimal data like human connectome data, but stuff that we just collect. What can you do with it? Like, what's the extent of what's possible, even with all the corrections and all that kind of thing? How far can you really go, like tractography wise?
Well, I guess it depends on your research question, right? So you can do lots of things with the data, but obviously you have hopefully a question in mind. And then obviously, given that question, we can look at aspects of the data that will allow you to address this question, right? So if your question is about, crossing fibers, but you haven't got data to substantiate those, to use those models, then, well, you can't use those data for that question. If your question is more about, different regions in the brain, not even looking at tractography necessarily, then yeah, you can continue with those data.
So how do you know, that your data isn't good enough for things like crossing fibers? Like, is there like an equivalent? You have to have this much or this good of data to be able to do this.
Well, so there's kind of guidelines. Again, it's not an exact science. It also depends on your data quality. So you can imagine having data sets with, let's say, even 30 directions and a b-value of 1,000, and maybe some quality aspects related to that data will allow you to do, these crossing fiber models, but sometimes it doesn't, right? So it depends on your SNR and all these things. And one way to find out is just, go to one of these software tools and try it. And if it looks plausible, then you're already, going in the right way. Okay, so So there's no exact yes or no. You just have to look at the data and just try it. Okay.
I'll just add, perhaps more optimistically, if you're looking at legacy data, you probably have a particular population that you want to study, because if you just want to study the healthy brain, there's a lot of fairly high-quality data sets out there. And if you apply some post-processing, some model to it, and you see a difference between two populations, then there's probably a difference. It might be hard to say what that is, but there probably is a difference. And then you'll need to make some inference about what it is. If you don't see a difference, there still might be a difference if it's really bad data. So you do need to take that into account and maybe do some power analysis to see whether the kind of difference you expect would be visible with the data you have.
Thanks for the great talks. I have a question about the validity of the tractography, because you said that there are some spots, like thanks to your project, we know that there are some spots that we know people make mistakes, different research groups mark different tracks, and you said that we could go back to micro resolution or information from in vivo scanning to kind of know that if those tracks are there or not, but I think that not all of us have access to, let's say, 9.4T scanners or in vivo imaging, ex vivo imaging. So I have a question about inter-subject variability, because in my data set I would have to use information from individual subjects from different cultures. Can I use that as an argument that tract is really there? Like, what's the limit of the inter-subject variability in those tracts?
Okay, I can say something about inter-subject variability. In tractography, subject variability is huge. And it's because maybe the FA is not high enough. So for example, the arc fascicle on the right side sometimes is not entirely visible or is missing, but not because it's not there, simply because the microstructure properties are very different from the left side. We still trying to understand what is going on. And some subjects are quite bilateral, other subjects, as I said, are very asymmetric. So I'm not sure you can use this inter-subject variability as a criteria to say, oh, the track is real or not, because we know the arc fascicle is real and is there, but for example, if you just use DTI for some subject, it's really hard to dissect. So the problem is the other way around, is why I don't say it, okay? Again, my answer is always the same. Try, look at the literature, try and see other modality, postmortem dissection, functional study, clinical study. Clinical study are very important, because if you have a lesion on your in your track, and then you have a immediate kind of functional disability or something going on correlated with that, that means that, oh, probably that track is real, okay? So that's usually clinical anatomical correlation, probably one of the most strong tools we can use to validate something without actually having a gold standard to compare with.
Thank you. Can I also would like to add here. So I would say that tractography is not easy. That's really something that you need to learn, and you need to have a lot of experience that everybody knows here. If you want to get some insight in the challenges when you do tractography, how does a track actually looks like, then there's a fantastic work by Sharma and Pandey that I think in 2006 or something, they make a great tracer study in monkeys, where you actually can see many of the major tracks. And they also been in this. It's like a big fat book where they have outlined the projection of the labeled axons, and there you can get a very good impression of how does a track actually looks like, and that is useful information when you go to the human tracking, and then you can take that data set or take that book, and then on our homepage we have a whole brain ex vivo setup where you actually can try out this kind of tracking in the same kind of brain that this atlas has. So that could be one idea of getting insights, what is true and false.
Okay, so we just have to hope that the reviewers have the same opinion.
Well, I think they will have that. Why shouldn't they have that?
I don't know. But yeah, that's a great start.
Just
if it's in the literature.
But yeah, but I think one of the things is when you do tractography, I think it's very important to be very clear how you extract the tracks. Because as we've seen, there are so many pitfalls, there are so many opinions of how to do things. So when you write up your stuff, very clearly, explicitly, how did you do it? And then, of course, there can be, we can agree and we can disagree. But the thing is, to be honest, how you actually obtain your results. I think that's the most important thing when you're communicating tractography.
Yeah. Thank you very much.
Okay, I think we have time for a final question, unless you are very quick, both of you. Okay, quick question?
Yeah, quick question. It's for quality control, and it's specifically for TBSS. Like I see a couple of issues being listed there, and it's kind of hard to like really examine everyone given the time scale or something. So can you like quickly comment on the like major points or what is more important if it is only for TBSS?
Well, so a quick sanity check I would do is that let's assume you've run the analysis pipeline and you end up with some region that shows significance between two groups in terms of some diffusivity property. Then go to that area and just look at how well does it actually align across subjects. If you can see that, hey, in some subjects the back projection, because you can compute all these warped maps, and you can just look at the region. And at least if you're kind of happy with that, well, it's indeed exactly in the same region across the different subjects between the different groups, then that would be a kind of sanity check to at least have greater belief in that this is a valid, significant difference, for instance.
So it's about subject alignments across groups?
Yeah, I think that's still the major issue in terms of validity of such a voxel-wise analysis. Okay?
Okay, last question.
So my question is about comparing different models, methods, or tractography algorithms, whichever. Basically today I think we are at a place where we always have to add a statement in the end. Okay, this comparison is very specific to this data, or this comparison is very specific to this sampling protocol. In your slides you showed that different models have different optimal protocols. And today we have these big data sets, right? And we're doing comparisons on those data sets. How do we it's not a global comparison, that's my understanding. It's a very specific comparison to that protocol, or even as you specified in your tractography talk that we didn't even know about that track until more recently. So even histology is something, there's a conditions applied to all these comparisons, right? So really how do we know what is the best, or what's your take on how the community has to go towards answering this question of maybe coming up with this ultimate algorithm, or really the most accurate model, or how, or a design for a really good protocol, sampling protocol?
Okay, so thanks for the short question. And there were actually a zillion questions in there, and that makes it really difficult, and that's why I guess we're all still in a job, right? I mean, I think it's, the field is moving forward so quickly, and there's many new models that are being generated, literally hundreds of different approaches to model the diffusion. I mean, some people call diffusion imaging confusion imaging, because there's so many degrees of freedom there, right? And so I think it's a long-term thing where, as a society, we move forward, and every 3 years we have a diffusion workshop, and we try to really go forward there. But it's so difficult because there is no absolute ground truth there, and that makes it so complicated.
But we are getting better. Okay.
Thank you. I need to go. So.
Okay, I think that we finish here. I'll see you later in the afternoon for the second session, and Anton Bire Alfrander will be the chair of the session. And okay, have a good lunch. See you later.